So now that we know how to simplify radicals, we're going to look at performing operations on radicals. So addition, subtraction, multiplication, division. And we're actually going to start with multiplication because that is the most straightforward of the operations. And we've already done this to a degree. So let's take two radicals and multiply them. And the thing to remember here is that multiplication, if you remember, is really just exponents, and it's the distribution property of the exponents. So remember that square roots is raising something to a half. So if you're raising something to a half, and you have a to the 1/2, b to the 1/2, then what we're really saying is that that's the same thing as a times b to the 1/2. Or square root of a, square root of b is the same thing as square root of a times b. The other thing I'm going to mention about these operations on radicals is that for multiplication, for division, we're primarily talking about square roots. When we're adding or subtracting, the index is not going to matter that much, whether it's cube root or fourth root, that won't matter that much. But here, same rules apply if the index here were not 2. So remember, the index is what's inside this little v. And if we do not see an index, the index is 2. So if the index were 3, the same rule would apply. Okay, but we're going to look primarily at square roots. So here, let's take two examples just so that we're clear. If we have the square root of 10 times the square root of 5, okay, when we multiply these, because ideally you want everything in simplest form would be the least radicals possible. You never want two radicals. We would multiply this. This would give us square root of 50. But the square root of 50 is not in simplest form, okay? We want only one radical, but we want it to be simplified. And 50 can be simplified further. So square root of 50 is the same thing as square root of 5 times the square root of 25 times the square root of 2. And we know that the square root of 25 is 5. So this is just 5 times the square root of 2. There are different ways of doing this. Here we multiplied first and then we simplified. We could theoretically simplify first. So another option for this, and I actually personally am not a fan of this option, but some of you, particularly if your multiplication, you like to keep it simple and you like using prime numbers, some of you may prefer this method. So your other method is to take this and put each one in its simplest form using what we call prime factorization. So prime factorization would be the breaking down a number into the product of its prime numbers. So for example, 10 is 5 times 2. 5 and 2 are both prime. So we can say that this is the same thing as square root of 5 times the square root of 2 times the square root of 5, which is really just, we have 2 square roots of 5s. And the square root of 5 squared is just 5, right? Okay, this is, if you did not understand this method, just ignore everything I said, okay? You don't have to use this method. It's not something that I typically prefer. Square root of 5 times square root of 10 times square root of 2 is the square root of 10. That's where that came from. So we just took the square root of 10 and we broke it down into 2 factors. And because the square root of 5 is repeated, we can just take that out of the square root and it becomes 5 root 2. So you get the same answer, it's just using a slightly different method. Let's do a second one. If we have the square root of 6 times the square root of 3, okay, we can multiply these and we get the square root of 18. But again, you want to make sure that it's in simplified form. So simplified form meaning you don't have any factors that are a perfect square. Here we do. This could be broken down into square root of 9 times square root of 2. And then the square root of 9 is 3. So this is 3 root 2. Okay, and using the other method, if you don't want to deal with larger numbers and you only want to deal with the small numbers that you're given, square root of 6 can be broken down into square root of 3 times square root of 2, or square root of 2 times square root of 3. So here's your square root of 6. But then don't forget you're multiplying that by square root of 3. So you have square root of 2 times square root of 3 squared. And the square root of 3 squared is just 3. So you get the same answer. You're just breaking that square root of 6 down into simpler factors before you do your multiplication. Okay, so it's kind of like you're taking this, simplifying it, and then you're multiplying. Okay, that's multiplication. There's not all that much to it. The reminder that I'll give you is that you always want to check to see if the radical in your final answer can be reduced. And this is actually the case for any operation. So as we work through addition, subtraction, division, you should always be looking for this. Okay, and we did that here because we said, okay, well, we get square root of 50, but that's not a final answer because it's not reduced. We have a perfect square that's a factor. Same thing with square root of 18. We have a perfect square that's a factor. And if you're having trouble reducing, go back to the previous video. Okay, so that's multiplication. Let's do addition and subtraction. The rules for addition and subtraction are the same, so we could talk about them simultaneously. Okay, so let's take some simple examples and then we'll add to it. So let's start with 2 times the square root of 3 plus 5 times the square root of 3 minus 3 times the square root of 3. Okay, now think of your square root of 3 almost like an x. You're combining like terms here. 2 plus 5 is 7. You're then subtracting 3. That gives you 4. So this is 4 square root of 3. And actually, I'll put that in red so that you see it as the answer. So notice right here, this is a one-step problem. Okay, so this is similar to 2x plus 5x minus 3x is equal to 4x. We're talking about combining like terms. So what we're doing is we're adding or subtracting the numbers outside the radical, which are called, those are our coefficients. So let's just do a couple more examples, and you should be stopping the video, trying it on your own, and then starting it up again. Okay, so if we have 8 square root of 7 plus 5 square root of 7, this is a one-step problem. All we're doing is we're saying, okay, square roots, the radicands are the same, so 8 and 5 is 13. We're just adding the coefficients. So this becomes 13 square root of 7. Okay, you could take another one. Let's say that we have 6 root 6 minus 2 square root of 6 plus 8 square root of 6 minus 3 square root of 6. Okay, well, this is very similar. All of these radicands that you see are the same. So that square root of 6 is just going to carry on through. Now we have to add and subtract these coefficients. So 6 minus 2, so we're only looking at these coefficients. 6 minus 2 is 4, plus 8 is 12, minus 3 is 9. So remember that you go left to right all the way through, okay? Left to right. So 6 minus 2 plus 8 minus 3. Okay, let's make this a little bit more complex. So in all of these cases, we kept it simple because we just have square roots. And the radicand, the number that's underneath the square root, is always the same. So we can just add the coefficients. Okay, this is actually always going to be the case. You cannot add or subtract in any other case. So let's write this down. We can only add or subtract if the following is true. The radicand has to be the same, which is the case here. In the first problem, the radicands were all 3. In the second problem, the radicands were all 7. And in the third problem, the radicands were all 6. That's not the only thing that has to be the same. The index has to be the same. So the index of all 3 of these problems was 2. If the index is different, you can't do anything. And then finally, the coefficients are like terms. So we'll go through examples where this is not the case. But if, for example, this had been 6x instead of 6, you could not have added or subtracted the 2. Okay, so either this is 6, no, so all of these are constants out here. If this had been a 6x, then it would have been 6x root 6, and then you could have combined these last 3. So we'll go through a couple of examples like that. Okay, so let's go through some more. These are going to be just a little bit more complex. And we're just going to do a whole bunch. Okay, so in this one, let's say that we have square root of 12 plus 5 square root of 3. Now, if you look at this, the problem is okay, our index is the same, but the radicands are not the same. So if the radicands aren't the same, we can add, okay? But don't just give up here, because it's possible that we will be able to reduce one of these radicals. And we can, right? Square root of 12 is not in its simplest form. So let's write that down. So here, the radicands are what's different. So we can't add yet. What you want to do is you want to check to see that all radicals are in simplest form before just giving up. So they're not here, right? Square root of 12 can be reduced to square root of 4 times square root of 3. And square root of 4 is 2. So now we have 2 root 3 plus 5 root 3. So do your check. The radicands are the same. You have 3 and 3. The indexes are the same. We have 2 and 2. Remember, no index means an index of 2. And our coefficients are like terms. We have a 2 and a 5. We can add 2 and 5. Okay, so this is just 7 root 3. So from here, the radicands are the same. The index is the same. And the coefficients are like terms. So we know that we can add at that point. Okay, so again, before giving up, make sure that you reduce your radicals. Okay, let's take another one. And this is really all you have to do. There's nothing new that I'm adding in. The only things that I'm changing now from here on out are, okay, well, maybe our coefficients aren't like terms, or maybe the radicands aren't the same. Maybe the indexes aren't the same. How do we deal with that? But the way that we deal with all of these things is to reduce the radicals as much as possible and then add what you can. So we're never going to be doing anything other than reducing, which means that as we go through each of these problems, stop the video, try it yourself, and if you run it into trouble, make sure that your radicals are reduced. And if your radicals are reduced and you still have trouble, not all 3 of these are met, then chances are is you can't add them and you have to leave it as is. Okay, so let's keep going, and again, try it on your own first. So our next one is going to be 4 square root of 8 plus 2 square root of 32. Okay. The radicands are not the same. Indexes are. So we know that once you see that the indexes are the same, then you really should figure, okay, the indexes are the same. It's likely that I will be able to add these, so certainly try to reduce. Okay, so we can reduce these. And I use the word reduce because the numbers under the radical are getting smaller, and reduce means to get smaller. So that's why I'm using that word. Okay, so square root of 8 can be broken up. We do have a perfect square that's half a factor. So this is going to become 4 root 2, and then plus 2 root 16 root 2. Because 13 is 16 times 2. 32 is 16 times 2. So now we have 4 times square root of 4. Well, 4 times square root of 4 is 2. So 4 times 2, root 2, plus 2 times 4, root 2. 4 times 2 is 8. 2 times 4 is 8. Okay, notice we just multiply here. 4 times square root of 4, well, square root of 4 is 2. 4 times 2 is 8. 2 times square root of 16, square root of 16 is 4. 2 times 4 is 8. Now, our radicands are the same. They're both 2. Our indexes are the same. They're both 2. And our coefficients are both constants. So they're like terms that can be added. So this is just 16 root 2. Now, in terms of how much work you need to show, you do not need to show every one of these steps. So of the first 2, choose one. I don't care which one you choose. Choose one to show. Okay? And then you could skip this third step. I prefer that you put it in just in case your multiplication is off. It's easier for me to see what happened, how you got this number. Whereas if your multiplication isn't off, if your multiplication is off and you skip this step, this third step, sometimes it can be hard to know exactly what happened, whether it was you didn't know that you had to multiply or you added or something went wrong. So I would say in terms of how much work to show, choose one of these first 2 steps and then show the third and the fourth. Okay? Okay, let's do another one. Five square root of 28 minus 3 square root of 63. Okay, right now the radicands are not the same. We have 28 and we have 63. So right now it can't be subtracted. So let's try reducing. Square root of 28 can be reduced. 28 can be divided into 7 and 4. I like to put the perfect squares first, just for elegance and the way that we write it, but it doesn't matter. Multiplication is commutative. So we have 3 square root of 9 square root of 7, and you can see that we do wind up with the same radicands here. Okay, 5 times the square root of 4. Square root of 4 is 2. I'm writing out both of these steps just for your benefit, but again, you can skip one of them. Then we have 3 times 3 square root of 7. That gives us 10 square root of 7 minus 9 square root of 7. And that's just equal to the square root of 7. Okay, let's try another one. Let's say that we have 2x squared square root of 5 plus 3x square root of 5. Okay, the radicands are the same here. The indexes are the same here. The problem is that the coefficients are not the same. Now, if the coefficients are not the same, you're going to still look at the radicands and you're going to say, can these be reduced? Can we reduce the radical? Now, here we can't. Okay, remember, you're always checking for this. We can't reduce the radical, which means that we can't add these. There's nothing to do. If you can't reduce the radical, there's nothing to do. Okay? So your answer is just, this is 2x squared square root of 5 plus 3x square root of 5. So the coefficients are not like terms. We checked to see if we could reduce the radical. But we can't, so we can't add or subtract. We can't add in this case. So we just leave it alone. Okay. Now, checking to see if we can reduce the radical is really important because in some cases, and you'll see examples of this very soon, in some cases that changes the coefficient, right? And you've already seen it. It's just that you haven't seen it with variables in there. So we've seen that this 4 turned into an 8. Well, it's quite possible that a 4 could turn into a 4x. Okay, it's quite possible that this 3x could turn into a 3x squared. You saw that when we simplified radicals in the last video, that our coefficients just changed completely. Okay, let's take another example. And this time, let's change the index. And again, most of the time, we're going to be working with the indexes of 2, but it doesn't really matter what index it is. So let's take 8 times the cube root of 16. So be careful with your handwriting here and make sure that it's clear that that 3 is an index. Plus 7 times the cube root of 54. Okay, so here we're going to reduce the radicands. The coefficients are like terms. The indexes are the same, but the radicands are not. So we need to try and reduce them. And 16 and 54 both have factors that are perfect cubes. Okay, so we can reduce this. So the cube root of 16 is the same thing as the cube root of 8 times the cube root of 2. Remember, you divide it into the perfect cubes and then what's left over. And then the cube root of 54 is the same thing as the cube root of 27 times the cube root of 2. So the cube root of 8 is 2. And the cube root of 27 is 3. Multiply out your coefficients. 8 times 2 is now 16. So we have 16 times the cube root of 2. And we have 21 times the cube root of 2. So now our indexes are the same, the indexes are the same, and the coefficients are like terms. So radicands are the same. You're always asking yourself this. Index is the same. Now they are. Coefficients are like terms. Now they are. Okay, and this applies to this last step here. So now all we have to do is add the coefficients. And that's our final answer, 37 cube root of 2. Okay, so you're always checking for those 3 things. Okay, let's take another one. So we have 2. Let's use an index of 3 again. Cube root of x to the 8th, y to the 6th, minus 3y squared. Cube root 8x to the 8th. Okay, so remember, you want to try and reduce. That's always going to be your first step. However, and this is not coming up here, if the index is different, don't bother because you cannot add or subtract. Okay, so you want, I'm going to write that down here. Always try to reduce the radicals unless the index is different. Okay, if the index is different, if reducing isn't going to make a difference, you still will have different indexes. Okay. And this actually goes for multiplication as well, that if the indexes are different, you're not going to be able to multiply that. Your indexes are the same here. So if we go back to here, notice your indexes are the same. If one is a 2 and the other is a 3, you can't use this distribution property. Okay, let's go back to the one that we were working on. So in the one that we were working on, we can reduce. Okay, there are factors that are perfect cubes, so let's try and reduce these. The indexes are the same, so it's worth reducing. Notice the coefficients are not like terms, but we're not going to worry about that yet. We worry about that after we reduce, after there's nothing else left to do. So each one we break up into perfect cubes, and then what's left over. So we have the perfect cubes for x to the 8th, y to the 6th. And then what's left over. So x to the 8th, we're looking for the largest power of x that's less than or equal to the exponent and divisible by the exponent, by the index. So 8 is not divisible by the index. We go down by 1. 7 is not divisible by the index. We go down one more. 6 is. So x to the 6th is going to go under here. And what's left over are 2 x's. We use 6 of them. There are 2 left. Okay, y to the 6th. Y to the 6th is, 6 is divisible by the index. So the whole y to the 6th goes under here. Okay, now we're going to do the other one. So we have minus 3y squared. And we're going to divide this up into perfect cubes and into the non-perfect cubes. Okay, so we have 8. 8 is a perfect cube, so 8 is going to go under, the whole 8 is going under this first one. Then we have x to the 8th. Well, x to the 8th we already know can be broken up into x 6th under here and x squared under here. Okay, so let's keep going. Now we have our perfect cube. So we just take the perfect cube. This cube root of x squared we can't do anything with. So now we have 2. Take the exponent and divide by the index. 6 divided by 3 is 2. So this gives us an x squared. Same thing with the y. 6 divided by 3 is 2. So we have a y squared. And then we have the cube root of x squared. Okay, now the other one. We have our 3y squared already there. Then we're reducing. Cube root of 8 is 2. Cube root of x to the 6th, well, 6 divided by 3 is 2. So we have a 2x squared. And then that cube root of x squared just stays. Okay, so let's continue. This first term is in its simplest form. We don't have to do anything. 2x squared y squared, cube root of x squared. The reason why I'm putting this step in is that the second term, we have numbers that can be multiplied. So 3 times 2 is 6. And we have an x squared and a y squared. I'm going to switch the order just so that you see it looks exactly the same. So we wind up with 6x squared, y squared, cube root of x squared. And now the index is the same, 3 and 3. The radicand is the same, x squared and x squared. And the coefficients are like terms. Why are they like terms? Because the powers of all the variables are the same. And I don't mean the power of x and y. I mean the powers of x are both 2. The powers of y are both 2. Okay? That's what makes them like coefficients. So these we can subtract. 2 minus 6 is negative 4. Negative 4x squared y squared, cube root of x squared. So here, we checked our index. The index was the same. Always check that first. The radicands are the same here. And the coefficients are like terms. So like terms, of each variable is the same, the exponents. So x squared and x squared, or y to the 5th and y to the 5th. Okay, so again, just to be clear, we're not saying that the exponents of the x and the y are the same. We're saying all of the exponents for the x are the same in every term, and all of the exponents for the y's are the same in every term. Okay, just to be clear, because I realize that we have a 2 and a 2 here. Okay, and we'll see that in our other examples. So let's take another one. Like I said, we're going to go through a lot just so that you get really accustomed to it. So I have 4 more for you. So the next one, we have 5x squared, cube root of x, y to the 4th, and then minus 2y, cube root of x to the 7th, y. Okay, so notice the index is the same, which means we should keep going. Once the index is different, just stop. Okay, but the index is the same. So we keep going, we reduce. So take each one individually and reduce it individually. So we have 5x squared we're dividing this into perfect cubes, and then what's left over? So we have x to the power of 1. Here, the power is already less than 3. So we can't put anything as perfect cube. X is not a perfect cube. So the whole x is going to go into the second one. Y to the fourth. 4 is not divisible by 3. We go down by 1. 3 is divisible by 3. So we're going to put a y cubed over here. And there's one y left over. Now we have a 2y, and we're going to do the same thing with this one. We're going to break it up into a perfect cube, and then what's left over? So we have x to the 7th. Well, 7 is not divisible by 3, so we go down by 1. 6 is divisible by 3. So we're going to have an x to the 6th under here, and there's one x left over. Okay. Now we have y to the first, and that's the same problem as the x over here. 1, which is the power of y, is less than the index. So the whole thing goes over here. Okay, now we're going to reduce. And I want you to notice even here, you know that you're most likely going to be able to subtract because you wind up with the same radicand. But you don't make any assumptions. You still want to make sure that your coefficients are the same. So we get 5x squared, and then the cube root of y cubed, 3 divided by 3 is 1. So we just get 5x squared y. And then the cube root of x times y. Over here, we get 2. And then x to the 6th, the cube root, 6 divided by 3 is 2. So I can put the x squared before the y. Or I could put it after, it doesn't matter. But for elegance, in other words, because it looks nicer, put the x squared first. Same thing, cube root of x to the 6th is x squared. Multiplication is commutative, so we could switch the order. And then we have the cube root of x times y. So now, at this point, our radicands are the same. The indexes are the same. The coefficients, they are like terms because you have an x squared and you have a y to the first in both terms. Okay? We have x squared, y, y, and that's it for variables. There's nothing that's different. So the only thing that should differ is the coefficients. And that's the case here. Okay, in this case, we have a 5 and a 2. So 5 minus 2 is 3. So this just becomes 3 x squared y times the cube root of x times y. Okay. So, and I'll put in here, the radicand we said is the same. The radicand is xy. The index is the same. The index is 3. Okay. Okay, let's do another one. Sorry, you can't see. 5a squared square root of 27 ab cubed minus 6b square root of 12 a to the 5th b. So here we check the index. The index is the same. It's a 2. When there is no index, it's a 2. So we can move on. So our next step is to simplify. Okay. And these are square roots. So we're looking for perfect squares. And then our what's left over for each one. So the 5a squared just stays. And then we have square root. Perfect square, what's left over? So 27 does have a perfect square as a factor. It has a 9. So 9 times 3 is 27. Now a, the exponent of a is 1, which is less than the index. So the whole a has to go into what's left over. And b, well, 3 is not divisible by 2, but 2 is. So we get a b squared under perfect squares, and there's 1b left over. Now we're going to go to the 6b side. So minus 6b, and then we're going to have our perfect squares versus what's left over. 12 does have a factor that's a perfect square. Its factor is 4. 4 times 3 is 12. So notice for the constants, we're talking about multiplication. a to the 5th. Well, 5 isn't divisible by 2, but 4 is. So a to the 4th is going to go under the first one. What's left over? 1a is left over. And then b has an exponent of 1 that's not divisible by 4. It's less than the index. The whole thing has to go under here. And now we just reduce. So we have 5a squared. Square root of 9b squared. Well, the square root of 9 is 3. And then 2 divided by 2 is 1. So we have b to the 1st. The 2 divided by 2 came from taking the exponent and dividing by the index, which is 2. And then we have square root of 3ab. Okay, minus 6b. Square root of 4 is 2. And then if we take the exponent, a to the 4, 4 divided by 2 is 2. So we get 2a squared. Square root of 3ab. Then we're just going to multiply. 5 times 3 is 15. So we get 15a squared b. Square root of 3ab. And then we get 12a squared b. 12 came from the 6 times 2. Okay, again, our index is the same. Index is 2. Radicand is the same, 3ab. And our coefficients do have like terms. The power of a is 2. The power of b is 1 in both of these. So now we just subtract. We subtract the coefficients. 15 minus 12 is 3. Now, if at this point, at this step, any of these have been different, if the radicands have been different, we would stop. We can't do anything. If the coefficients had not been like terms, we would stop. We can't do anything. This is it. We would stop at this step. Okay? And if the indexes are different, we wouldn't even go past this first step. Okay. 2 more. Let's take 7 times the cube root of a cubed, b cubed. Sorry, not a cubed, a to the 4th. A to the 4th, b cubed, c squared. Minus 6ab cube root of ac squared. Okay. The indexes are the same. So because the indexes are the same, we move on to the next step and we simplify the radicals. Okay, so that's always the case. That's what we've been doing so far. Index is the same, simplify the radicals. So the first one, we're dividing it into perfect cubes and non-perfect cubes. So a to the fourth, 4 isn't divisible by 3. Go down by 1, 3 is. So we have a cubed. There's 1a left over. For b, 3 is divisible by 3, so the whole b cubed goes under this first one. And for the c, well, 2 is less than the index, so the whole c squared has to go under here. Okay, then this, in the second term, both of the exponents are less than the index, so it can't be reduced anymore. So we just leave it. Both exponents are less than the index, so it can't be reduced. So we get 7. 3 divided by 3, this is a 3. 3 divided by 3 is just 1, so we get 7a. And same thing for b, 7ab. Cube root of ac squared minus 6ab. Cube root of ac squared. And at this point, the index is the same. You should never, if you've gotten to the point where you're reducing, your index should be the same. You should never get to that point if your index is different. Our radicand is the same. It's ac squared here. And our coefficients are like terms. The power of a is 1 in both cases, and the power of b is 1 in both cases. So now we could just subtract. 7 minus 6 is 1. So we get AB times the cube root of AC squared. Okay. Again, at this point, if either the radicand or the coefficients is different, okay, where the radicand is not the same under here, you would stop. If the coefficients weren't like terms, so for example, this were 7AB and this were 6AB squared, you would stop. Okay, you cannot go ahead if there's any difference. Okay, let's do one last one. (3a) 4th root of a squared b to the 8th plus 2a squared cube root of a to the 7th, b to the 10th. So what do we check for? Always check the index first. The index is different, okay? Because the index is different, we can't do anything. You're not being asked to reduce. If you were being asked to reduce, then sure, you can reduce these. But if you're not being asked to reduce and you're just being asked to add, here the index is different, stop. Okay, so always check the index first. I may have written this already, but I'm writing it again. Always check the index first. Reduce only if they are the same. And if you have 3 terms and the index is the same in 2 of the terms, then yeah, add those 2 terms. But you can't add the 3rd term to it. Okay, so here you would stop. Okay, so that's addition and subtraction. Let's do division. So division seems like it would be harder, but it's actually really straightforward, because just like in complex numbers, you're not actually dividing here. All you're doing is you're getting rid of the radical. So in complex numbers, we wanted to get rid of the imaginary numbers. Here we would want to get rid of the radicals. And only in the denominator. We understand you're going to have radicals in the numerator most of the time. How do we do this? Just like in complex numbers. The only difference is that we don't call it complex conjugate. We just call it a conjugate. So what do? You multiply both the numerator and the denominator by the conjugate of the denominator. Just like we did when in complex numbers, we multiply by the complex conjugate of the denominator. Here we don't call it complex because it's not a complex number. And this gets rid of the radicals because your radical in the denominator winds up getting squared, just like the I got squared and it became a -1. Here, when you square a conjugate, okay, when you square a radical, you get rid of the radical. So this process, we'll do an example of that in a second, but this process is called rationalizing the denominator. The reason why we call it that is because a radical is an irrational number. So if you get rid of the radical, then what you're doing is you're rationalizing. You're coming up with a denominator that is rational, okay? So anytime that you hear us say, please rationalize the denominator, what we're doing is we're saying, make sure that you take out any square roots. So just as a note here, okay, why does this work? Well, 3 plus the square root of 2, let's show this by example. The conjugate of 3 plus the square root of 2 is 3 minus the square root of 2. So remember, the only thing that changes sign is that second term, what's in the middle. So this is the conjugate of 3 plus square root of 2. So if we multiply this out. 3 times 3 is 9. Then we have 3 times negative square root of 2, or negative 3 root 2. 3 times the positive square root of 2, or plus 3 root 2. And then square root of 2 times negative square root of 2, which is negative 2. So these middle terms cancel, and you get 7. There's no radical here. That's always the case because those middle terms cancel, okay? When you do it for FOIL, if you use FOIL, when you multiply the first terms, the outer terms and the inner terms, okay? The outer and the inner cancel each other out because they're the same when you multiply them. So because they cancel each other out, and when you multiply the last, you have radicals. So a radical squared gives you an integer. You're getting rid of any radicals that are inside that denominator. Okay, so we'll do 3 examples here because they're all essentially the same, and it's multiplication, and it's just multiplication. So let's say, for example, that we have 2 over 3 plus the square root of 5. Okay, so to do this, all we're going to do is we're going to multiply both the top and the bottom by the conjugate of the bottom. So the conjugate of 3 plus root 5 is 3 minus root 5. Notice you have to multiply the top and the bottom by the same thing so that you don't change the value of this expression, okay? This is an expression, so the only way to keep it the same is to multiply by 1. If we have to multiply the bottom by 3 minus square root of 5, then in order to keep the expression the same, we also have to multiply the top by 3 minus square root of 5. So that what we're really doing is we're multiplying by 1. Now we just multiply. 2 times 3 is 6. 2 times negative square root of 5 is 2 root 5. In the bottom, 3 times 3 is 9. That's the first. Then we're going to take, remember, every term gets multiplied by every term in the first set gets multiplied by every term in the second set. So we have 3 times 3 is 9. 3 times negative root 5 is negative 3 root 5. Then we have square root of 5 times positive 3, so plus 3 root 5. And then we have square root of 5 times negative square root of 5, which is just negative 5. These terms will always cancel. So if you want to take a shortcut, you can skip this step and you can just say, okay, well, this is 9 minus 5, because you know that those middle terms cancel. And that's okay to just say that they do. So this becomes 6 minus 2 root 5 over 4, because 9 minus 5 is 4. But we are not done. You must reduce, and everything here is divisible by 2. So this is really 3 minus square root of 5 over 2. This is your final answer. You must reduce your fractions. By checking to see if every term has a common factor. Okay, so in this one, we could divide everything by 2. because everything is really important. And notice we divided the 2 root 5 by 2, so it became square root of 5, not square root of 5 halves. Okay, let's do another one. So we have 6 plus root 5 over square root of 2 minus square root of 5. So in this one, we're going to multiply both the top and the bottom by square root of 2 plus square root of 5. I would always multiply out the bottom first just to make sure that you actually are getting rid of your radicals, because that way if you don't get rid of your radicals, then you know that you made a mistake and you're saving yourself work that you would have been doing on the top. So square root of 2 times square root of 2 is 2. Then we have square root of 2 times square root of 5, which is square root of 10. Then we have negative square root of 5 times square root of 2, or negative square root of 10. And then minus square root of 5 times square root of 5, or minus 5. The square roots of 10 do cancel, so we know that we did something right. Okay, now we can go to the top. 6 times the square root of 2 is just 6 root 2. Then we have 6 times the square root of 5, so plus 6 root 5. And then square root of 5 times square root of 5 is square root of 10. So plus square root of 10. I don't know why that 6 isn't coming out. There we go. And then square root of 5 times square root of 5, which is just 5. Okay, so if we look on top, we actually can't add any of these. The radicands are all different, okay? The indexes are the same, but the radicands are different, and there's no way to make these radicands the same, okay? Square root of 2 is in its simplest form. Square root of 5 is in its simplest form. Square root of 10 is also in its simplest form. There is no factor that's a perfect square. So our final answer actually leaves the numerator exactly as it is. It's 6 root 2 plus 6 root 5 plus square root of 10 plus 5 over negative 3, and we can't get any simpler. There are no common factors for all terms either. So this is in simplest form. And let's do one last one. So 3 plus square root of 7 over 5 minus square root of 7. So what do we do here? We multiply by the conjugate of the denominator. So the conjugate of 5 minus root 7 is 5 plus root 7. We do that on top and we do that on bottom. So let's do the bottom first, just to double check. 5 times 5 is 25. Plus 5 root 7 minus 5 root 7. And then negative root 7 times positive root 7 is minus 7. So these middle terms do cancel. Then on top we have 15 plus 3 times the square root of 7 plus 5 times the square root of 7. And then plus 7. So on the top we combine like terms. So 15 and 7 can be combined. And 3 root 7 and 5 root 7 can be combined because they both have radicals. Sorry, I don't know why they came out that way. They both have radicals. The radicands are the same, the indexes are the same, and the coefficients are like terms. So here we have 22 plus h root 7 and 2 minus 7, 25 minus 7 is 18. So we are not done because everything is divisible by 2. So we're going to divide everything by 2. And we get 11 plus 4 root 7. Notice we only divide the coefficient by 2 there. And that's because the 8 and the square root of 7 are being multiplied, not added. Over 9. So this is our final answer. Okay, here we can divide everything by 2. And that's it.